As scientists and astronomers peer more closely and with ever more fidelity at nearby stars, they are discovering exoplanets, worlds outside our own solar system. Stars with planets were once thought to be a rarity. They are turning out to be the norm and not the exception. With some confidence, scientists now calculate there could be as many as 40 billion Earth-like planets in our Milky Way galaxy alone. The first exoplanets were detected in 1992, orbiting a pulsar, the remnants of a massive exploded star that was now a fast-spinning neutron star. With data collected from the Arecibo antennae in Puerto Rico, Alexander Volshan discovered 3 terrestrial planets orbiting the pulsar PSRB 1257+12. Other pulsars have been detected with dust clouds and disks orbiting them. This suggests that these 3 planets are second generation. The original planets were destroyed by the stellar explosion, and the subsequent debris disk enabled these new planets to form. It was another 3 years before the first planet orbiting a G-class star similar to our Sun was identified, a gas giant like Jupiter orbiting 51 Pegasi every 4 days. 5 years later, another main sequence star was found to have multiple planets. Exoplanets were not easy to detect. They are tiny, their light smothered by the light of their star, and they are so far away. There are 3 main methods for planetary detection. The hardest is direct visual observation via telescope, both on the ground and in orbit. Some 59 planets have been discovered this way. More indirect methods are employed, one of which is the radial velocity method. As a planet orbits, its gravitational pull causes the parent star to move back and forth. This tiny radial motion shifts the observed spectrum of the star by a correspondingly small amount because of the Doppler shift. With supersensitive spectrographs, the shifts can be measured and used to infer details of a planet's mass and orbit. The 3.6-meter telescope at La Silla, Chile, has such a spectrographic instrument called HART and is the leading exoplanet hunter. This is Tau Boötis, one of the first planets discovered utilizing this method. 51 light-years from Earth, this planet is massive, some 4 times the mass of Jupiter. So far, over 600 planets have been detected by this method. Another observational tool, and the most successful to date, is the transit method. A planet that passes in front of its parent star relative to us produces a slight dimming of the star's light, which can be detected by sensitive instruments. Some 1,200 have been located this way. Until now, it was expected that exoplanets would orbit in more or less the same plane and in the same direction as the star's rotation. However, new results unexpectedly show that many exoplanets actually orbit at a large angle to their star's spin axis. In the case shown here, WASP-8b, the orbit is completely reversed. There are other tools and techniques in the planet hunting toolbox, including microlensing, occultation and TTV, or transit timing variation. Often more than one technique is used to verify findings. In fact, revisiting a planet after some time for verification can lead to surprising results, as in HD 189733b, a hot Jupiter-type planet. On revisiting it, Hubble discovered the atmosphere was being stripped from it by a violent stellar flare.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen. All for free. No subscription required.
With the Hubble Space Telescope dividing its valuable time between many varied tasks and objectives, a dedicated planet hunter called Corot was launched. The mission was led by the French space agency, CNES, with contributions from ESA, Austria, Belgium, Germany, Spain and Brazil. Launched in 2006, the mission lasted 7 years. It located 2 planets around the star Corot 7, one of which was the first found to display a density similar to Earth's. In all, it located 32 planets, and 100 others are awaiting confirmation. The NASA Spitzer infrared space telescope was launched to study protoplanetary and debris disks around stars and the curious brown dwarfs, often referred to as failed stars. Spitzer's infrared capability quickly led to numerous planetary discoveries and infrared mapping of other known planets, like hot Jupiter HD 149026b. Some 256 light-years away in the constellation Hercules, a planet dubbed a hot Jupiter, it is a sweltering 2040 degrees Celsius, the hottest planet yet detected, and also the darkest, reflecting no sunlight back into space. It speeds around its star every 2.9 days. A world just 2/3 the size of Earth, one of the smallest on record, and only 33 light-years away around the star GJ436, planet UCF-1.01 might be the nearest world to our solar system that is smaller than Earth. The planet, a rocky world, orbits so close to the star that the surface is probably molten. As with HD 189733b in the constellation Vulpecula, it appears to be tidally locked to its star, showing only one face as it orbits. Spitzer was able to distinguish the various temperatures of its clouds from 650 to 1700 degrees Celsius. Thermal imaging of these hot giants has provided more details of these distant worlds. In 2009, the game changed with the launch of the Kepler Space Observatory. As part of NASA's Discovery program, the Kepler Space Telescope was launched to survey and monitor a fixed field of stars of the nearby Milky Way trailing behind Earth. It observed around 165,000 stars, watching for any changes in their brightness. It has located over 1,100 planetary candidates.
Now these are candidates, but most of them, I'm convinced, will be confirmed in the coming months and years. That's more than all the people have found so far in history.
A veritable menagerie of planet types is emerging, like Kepler 16b, orbiting 2 stars, ice worlds and water worlds like Gliese 1214b.
The Kepler team announced today 1,094 new planet candidates, bringing the total roster up to 2,326. Of those, 207 are Earth-size, and we now have 48 that are in the habitable zone, 10 of which are smaller than 2 Earth radii. So these are planets that could potentially be rocky. So it's an exciting milestone because we are really honing in on truly Earth-sized habitable planets.
The combined surface and space-based system observations have led scientists to believe that planets around stars are the rule rather than the exception, and the average number of planets per star is greater than 1. Kepler has discovered at least 86 stars with multiple planetary systems. Kepler-11, for example, has 6 confirmed planets orbiting a Sun-like star.
The Kepler-11 planetary system is amazing. It's amazingly compact, it's amazingly flat. There's an amazingly large number of big planets orbiting close to their star. We didn't know such systems could even exist. There's certainly far fewer than 1% of stars have systems like Kepler-11. But whether it's 1 in 1,000, 1 in 10,000, or 1 in a million, that we don't know, because we only know one of them.
The growing number of confirmed planets is opening up new insights into planet formation.
We're learning so much more about the orbits of planets, the masses of planets, the sizes of planets, and we're just beginning. Kepler is still returning data, and we're going to learn a fantastic amount about the diversity of planets out there around stars within our galaxy.
Around each star is a circumstellar region called the habitable zone. Sometimes referred to as the Goldilocks zone, this is a region neither too cold nor too hot, where a planet could, under the right conditions, support liquid water at its surface, and in turn could support life. The first Earth-sized planet in a habitable zone was discovered around a red dwarf. Named Kepler 186f, it is just 10% larger than Earth.
Kepler 186f is the first validated Earth-sized planet in the habitable zone of its star. It's the outermost of 5 planets to orbit a star that is smaller and cooler than the Sun. This planet orbits its star every 130 days, and so this places it in the habitable zone, where it's in a region where it could have liquid water on its surface.
The star Kepler 186 is 500 light-years from Earth in the constellation Cygnus.
This planet, Kepler 186f, orbits a star that's cooler and dimmer than the Sun. So while we may have found a planet that's the same size as Earth and receives a similar amount of energy to what Earth receives, it orbits a very different star. So perhaps instead of an Earth twin, we've discovered an Earth cousin.
Believed to be a rocky world, its mass and density are yet to be determined.
This is one of the big milestones that we've been looking for in our attempts to find out if there are places just like home and if there's life out there. One of the big steps is to say, is there somewhere that looks, to all intents and purposes, like Earth? Well, we don't know just yet, but we know that there are places that at least look similar.
To date, over 48 Earth-like planets have been located within habitable zones. Gliese 581 has 4 known planets. The outer D planet is thought to be an icy planet that has migrated closer to the star and would thus be covered by a large and deep ocean. Kepler 62f is likely to have a rocky composition and is only 40% larger than Earth, making it the exoplanet closest to the size of our planet known in the habitable zone of another star. Kepler 62e orbits on the inner edge of the habitable zone and is roughly 60% larger than Earth. Other recent discoveries include Kepler 438b, 442b, and 440b, a super-Earth. The super-Earth exoplanet GJ1214b orbits its faint red parent star. This is the first super-Earth exoplanet to have had its atmosphere analyzed. It has a mass about 6 times that of the Earth and appears to be surrounded by an atmosphere of steam or thick clouds or haze. Based on observations, scientists believe that of the Sun-like stars, some 22% have an Earth-sized planet orbiting in the habitable zone. Assuming 200 billion stars in the Milky Way, that would be 11 billion potentially habitable Earths, rising to 40 billion worlds if brown dwarfs are included. Are any of these worlds close to Earth? In fact, yes. The closest star to our own is the well-known Alpha Centauri group, with the bright stars Alpha and Beta Centauri, plus the faint red star Proxima Centauri, the closest star to Earth. Alpha Centauri b is known to be orbited by an Earth-mass planet, making it the closest exoplanet to our solar system, a mere 4.37 light-years away, almost within our reach. Now in its fourth observing campaign, the Kepler spacecraft continues targeting 16,000 stars for exoplanets. It's estimated that the onboard fuel supply should last until at least December 2017. So far, Kepler has found an astounding 1,013 confirmed exoplanets around 440 star systems. The terrestrial telescopes continue to do the heavy lifting when it comes to verifying possible planet candidates. The HARPS spectrographic instrument at La Silla, Chile, is being joined by the Next Generation Transit Survey, or NGTS. It will search for transiting exoplanets with a focus on discovering Neptune-sized and smaller planets. NGTS is designed to operate in a robotic mode. It will continuously monitor the brightness of hundreds of thousands of comparatively bright stars in the southern skies. ESO's Very Large Telescope at Cerro Paranal in Chile, composed of 4 individual telescopes, will be improved with the new next generation of adaptive optic system called SPHERE. Other improved technologies include the Gemini Planet Imager at nearby Cerro Pachon, now in operation, and the Subaru Coronographic Extreme technology currently being installed and tested. New, bigger and more powerful telescopes are in the pipeline as well. The 30-meter telescope planned for Mauna Kea, Hawaii, will have 492 small hexagon mirrors arranged together to form the primary mirror 30 meters across. The GMT, or Giant Magellan Telescope, will be built at the Las Campañas Observatory in Chile. It will consist of 7 8.4-meter mirrors arranged together to make up the primary mirror. Work on the mirrors is well underway. The European Extremely Large Telescope in the Atacama Desert is due for completion in 2024. It will have a 39-meter diameter mirror made up of 798 hexagonal mirrors and will be the largest ever built. It will enable scientists to study the atmosphere of exoplanets more closely. Space-based telescopes are advancing as well. The next generation infrared telescope, James Webb, is nearing completion as it goes through rigorous testing. A scheduled launch in October 2018 will put the 6.5-meter telescope in orbit as a replacement for the Hubble and Spitzer telescopes. Likened to the California gold rush, there are planets out there to be found, and the race is on. TESS, the Transiting Exoplanet Survey satellite, is scheduled to launch in 2017. TESS will scan the entire sky, searching for exoplanets using 4 state-of-the-art cameras. It will be able to determine the chemical compositions of exoplanet atmospheres. Also planned for a 2017 launch is Cheops. Its function is to characterize transiting exoplanets orbiting bright host stars. The satellite is a small package, roughly 1.5 meters square, with a life expectancy of 5 years. The European Space Agency has commenced a new program called Cosmic Vision, set to run from 2015 to 2025, with Plato, an exoplanet hunter, expected to be launched in 2024. Other projects underway include Pégase, under development in France, Exceed, the Exoplanetary Circumstellar Environments and Disk Explorer at NASA, and Finesse, the Fast Infrared Exoplanet Spectroscopy Survey Explorer, due to launch 2019. The Wide Field Infrared Survey Telescope, WFIRST, is another NASA observatory designed to perform wide-field imaging for the planet-hunting community. It will be fitted with a coronagraph instrument for direct imaging of exoplanets and debris disks. Another NASA New Worlds mission is the Star Shade project, scheduled for a 2019 launch. It will physically block the star's light with a parasol to allow direct observation of exoplanets. NASA is already thinking about a future James Webb replacement. Called the Advanced Technology Large Aperture Space Telescope, or ATLAST, it will be 2,000 times more light-sensitive than Hubble. If all goes according to plan, ATLAST could be launched between 2025 and 2035. With these new tools and technologies, it is only a matter of time before we are able to detect Earth-like worlds capable of supporting life. Perhaps one day, even a planet emitting radio or other signals indicative of a sufficiently advanced intelligent civilization. Finally answering that great question, are we alone? It rises in the east and bathes our planet in light. It powers the machinery of nature, our weather, encourages and sustains life on land and at sea, where it warms our oceans from pole to pole. When it sets in the west, it reveals to us its many billions of sibling stars, populating the night sky. We study our sun closely, and like a Rosetta Stone, it can reveal the secrets of all the other stars. You cannot study the sun in isolation. The influence of its power throughout the solar system it created is persuasive and dominating. The heliosphere is an immense magnetic bubble extending beyond the orbit of Pluto. It contains the solar wind of high and low-speed energetic particles and plasma that originate at the surface of the Sun. After traveling for 36 years and 19 billion kilometers, the Voyager 1 spacecraft has reached the edge of this heliosphere.
Voyager 1 has left the bubble around the Sun and entered interstellar space, the space between stars.
There, it still senses the shock waves emitted by the Sun, which sound like this. To understand this source of power and its influences, scientists conduct observations from the ground and in space, where a flotilla of satellites train sophisticated sensors upon the Sun and the space weather it creates.
Space weather is the field that studies how what's going on the Sun affects us here on the Earth in our near space environment and on the space environment on other planets. The effects of space weather are so complicated because we have to understand what's going on at the Sun as well as all that stuff traveling through interplanetary space, how that affects us here on the Earth and throughout the heliosphere, that we need an entire fleet of instruments to look at these various effects. It's basically a system science, so you understand one part of it in order to understand the other part of it, and you have to put that whole puzzle together to understand the full effects of space weather.
GOES-P is an ongoing series of Earth observation satellites that happen to keep a constant eye on the Sun, monitoring this space weather.
So when the spacecraft's sitting in space, it's looking down at the Earth and it stays stationary like this. But this solar array out here moves and tracks the Sun, so that way it's always looking at the Sun and can take a scan every minute.
The Sun's outer atmosphere is constantly being heated up by the solar surface, and this causes particles from the Sun's atmosphere to stream away constantly. These streaming particles, which are filling our entire solar system, are called the solar wind.
Different phenomenon from the Sun is constantly bombarding the Earth. Although you might not know it, the solar weather affects you every day down here as well. Not only just astronauts, it affects people on Earth.
The latest generation of GOES satellite is the GOES-R, soon to be launched into orbit. Other low Earth orbiting platforms include ESA's microsatellite Proba-2, testing new technology, and PICAR, sponsored by CNES, the French space agency. Hinode is the Japanese word for sunrise. It is a joint mission between JAXA, NASA and ESA to study the Sun's magnetic cycles. Its close-up study has revealed the complex granular textures of the Sun's surface and insights into solar flares.
A solar flare is a huge release of energy that converts the magnetic energy of the Sun into heat, into light. It accelerates particles and can really heat up the plasma in order of minutes to over 60 million Kelvin.
For a large eruption, the Sun produces a flash of light, which we call the solar flare. It also produces a huge ball of material traveling away from the Sun we call the coronal mass ejection. And both of those phenomena can accelerate subatomic particles, which we call solar energetic particles. These three things together make up a solar storm.
To study the solar wind phenomenon, a group of satellites were placed in a unique orbit between Earth and the Sun at what is called L1, or Lagrange point 1, a point of gravitational balance between the Earth and the Sun. The Advanced Composition Explorer, or ACE, observes energetic solar particles. WIND studies radio waves and plasma that occur in the solar wind and in the Earth's magnetosphere, and SOHO, the Solar and Heliospheric Observatory.
using SOHO and using a technique called helioseismology, very similar to seismology on the Earth, we were actually able to see inside the sun. And so what we were able to do is see the layer of the sun just below the visible surface that we call the convection zone. And that's where all sorts of dynamics are going on. The inside of the sun is bubbling up to the surface. And that's really where all of the solar phenomena that we see is first developed. And so we were able to see underneath the surface and see these flows of solar plasma, see the formation of sunspots. And this is something that's never been done before. We're actually able to see the details inside of a star.
Another high-resolution space telescope was TRACE.
You're seeing details of the coronal loops. In the previous images you would from other satellites, it would look like it was just one big loop. And when you actually get to see TRACE, you can see it's all these teeny tiny, finely, they almost look like threads. And there's these teeny tiny loops, and they're just breaking off and reforming and throwing plasma.
Using X-ray and gamma-ray solar flare imaging, RISI explores the particle physics behind solar flares. Another event subjecting the solar system to bombardment is the CME, or coronal mass ejection event.
A coronal mass ejection, or CME, is an eruption of plasma from the sun that shoots out into space, and it could affect us here at Earth if that big ball of plasma were to hit us.
NASA's twin stereo mission has one spacecraft orbit the sun ahead of the Earth and the other behind, providing a stereoscopic view of the sun to better understand these coronal mass ejections and the energetic particles of plasma.
Solar energetic particles are particles of plasma that are accelerated at the flare site from the energy that's released in the flare, and these particles could be accelerated up to almost 80% of the speed of light.
And a coronal mass ejection, when it's traveling so fast, creates a shock, and that can create solar energetic particles.
In 2009, NASA commenced a new scientific program called Living with a Star. The crown jewel of this program is the Solar Dynamics Observatory, or SDO, the most advanced spacecraft ever designed to study the sun and its dynamic behavior. The program's goal is to develop the scientific understanding necessary to address those aspects of the sun that directly affect us here on Earth. The spacecraft provides 16-megapixel ultra-high-definition imagery of the sun in 13 different wavelengths. From extreme ultraviolet frequencies to the helioseismic and magnetic imager and the atmospheric imaging assembly, each wavelength was selected to highlight a particular part of the sun's atmosphere. The results are stunning. They reveal fine details from the solar surface to the upper reaches of the sun's corona. These solar events dwarf our planet, and the science has brought a renewed focus back to Earth's protective magnetic field.
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
Fortunately, we are protected here at Earth from flares and coronal mass ejections by the Earth's outer atmosphere. It absorbs a lot of the energy from the increased light from solar flares. But we're also protected by the magnetic field. You know, the Earth has a North Pole and a South Pole. Anyone who has a compass knows that. But this magnetic field of the Earth also protects us from these charged particles, the plasma coming from coronal mass ejections that largely deflects a lot of this direct energy. A coronal mass ejection will come and affect the Earth's magnetic field, and changing and hitting the Earth's magnetic field causes other changes on the actual far side, away from the Earth. that then accelerates more particles and shoots those particles then into the North and South Pole that produce these very beautiful waves of green and blue and red that are just lovely to see.
The sun is powered by a process called fusion, and that happens at the very core of the sun, where it is so intense, so hot, and so dense that protons fuse together and create helium. And this process fuels the sun and creates energy.
As the energy moves outward, boosted by magnetic fields, the temperature drops.
Up until that point, everything makes sense in that the hottest part is in the middle and everything gets gradually cooler as we move away. But then something very interesting starts to happen, which is that it starts to get hotter again.
This layer, where the temperature begins to rise again, is called the chromosphere. It lies between the photosphere and the corona, which is the hottest part of the sun's atmosphere. To discover how this corona is powered, another mission called IRIS was launched in 2013. IRIS carries a single ultraviolet telescope and imaging spectrograph, whose tight resolution allows it to see features as small as 240 kilometers on the sun's surface. IRIS's first images showed a multitude of thin fibril-like structures that have never been seen before, revealing enormous contrasts in density and temperature occurring throughout the region.
The light from the chromosphere is difficult to interpret because of the complicated interaction that the light has with the matter. It bounces around, if you will, many times before its final bounce towards us. And this means that that interaction between light and matter needs to be modeled in great detail, due to not just advances in computational power of computers, but in the computational techniques that have been developed by the IRIS team. We are in a position to do this.
Data collected from the IRIS spacecraft has shown that the interface region of the sun is significantly more complex than previously known.
Although the corona is extremely hot, millions of degrees, it's at a low density, so it doesn't actually take a lot of energy to heat it to that temperature. The chromosphere, on the other hand, is a much higher density, albeit lower temperature. And there's much more energy deposited in the chromosphere than the corona. So that a tiny fraction of that energy in the chromosphere escaping into the corona is plenty to power all of the processes that we see, from heating to such extreme temperatures to driving the solar wind that fills the whole solar system, impacting all the planets, including our own. We hope to better understand these fascinating and important processes with IRIS.
This energy streaming from the sun causes other knock-on effects on the planets of the solar system.
The northern lights are particles that are being shot into the North Pole and the South Pole that produce these beautiful greens and blues and reds. They're not direct particles from the sun. A coronal mass ejection will come and affect the Earth's magnetic field, and changing and hitting the Earth's magnetic field causes other changes on the actual far side, away from the Earth, that then accelerates more particles and shoots those particles then into the North and South Pole that produce these very beautiful waves of green and blue and red that are just lovely to see.
Armed with more questions about the solar wind and energetic particles, NASA launched a pair of probes into Earth orbit. Named after the famous scientist who discovered the radiation belt surrounding our planet, the Van Allen probes were dispatched to study the radiation phenomenon and the magnetic fields around the Earth in greater detail.
During the course of geomagnetic activity, disturbances caused by flares on the sun, by big blobs of plasma coming out from the sun towards the Earth, the Earth's magnetic field is battered and shaken. Some of that energy is captured in the Earth's magnetic field, and through a variety of processes, that energy energizes particles in the Earth's radiation belts up to energies that are hazardous to spacecraft and astronauts. The two spacecraft are focused on the dynamic radiation belts in the Earth's inner magnetosphere. They're the only spacecraft that focus on those. Consequently, they're a critical component in the series of phenomena that link the Sun to the Earth.
Solar flares and CMEs are all driven by magnetic reconnection. This is where the sun churns up the magnetic field that's inherent in it, and then it causes oppositely directed magnetic fields to then annihilate. But you can't just get rid of magnetic field. You can't just get rid of energy. You have to convert that energy and transfer that energy into other things, such as plasma motions, accelerating the plasma, heating up the plasma, and also giving out more light.
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
But this magnetic field of the Earth also protects us from these charged particles, the plasma coming from coronal mass ejections that largely deflects a lot of this direct energy.
The phenomenon of magnetic reconnection is not well understood, so NASA has launched a multi-satellite mission called MMS to try to unlock the secrets of our magnetic field.
The MMS mission is a mission consisting of 4 spacecraft which will fly in close constellation to measure a process called magnetic reconnection.
The universe is full of plasma and it's full of magnetic fields, and all over the place in the universe you have one plasma colliding with another. An example of that is the solar wind coming in and colliding with Earth's magnetosphere. And then the magnetic energy in the plasma, some fraction of that magnetic energy is converted very rapidly into plasma energy. So you can think of it as kind of like a magnetic explosion. And the reason this is important is because these explosions drive a lot of the weather patterns that we see in the magnetosphere, and so what space scientists like to refer to as space weather. And these space weather phenomena can have impact on our everyday lives. It can actually affect communication satellites, the power grid. So we'd really like to understand how these magnetic explosions work.
We need to measure reconnection in more than one location. We need to measure it in basically how it varies in space, how it varies in all 3 spatial dimensions. And that requires a tetrahedron. The additional fantastic benefit that provides is that it will actually enable us to recognize that we're looking with a reconnecting region much easier than a single spacecraft.
The ideal situation is that we would like the 4 spacecraft to kind of be surrounding this region where the explosion is happening. So the separation of the spacecraft is about 10 to 100 kilometers, which may seem like a long distance. But in terms of the magnetosphere, which is absolutely huge, this is really a microscopic region that we're trying to cover.
MMS has, in a nutshell, 2 orbital phases which are designed to study reconnection.
On the day side, basically you have a situation where the solar wind is just constantly running into Earth's magnetic field. And this is really great for MMS because we know that at some point MMS is going to encounter this region, and our hope is that since this process is always happening, we're going to get lucky and actually fly right through the magnetic explosion as it's happening. Now on the night side, the situation is a little bit different. So what happens is you have a more gradual buildup of magnetic energy in the tail, and these reconnection processes, these magnetic explosions, can just sort of pop off randomly. We don't really know when it's going to happen or where it's going to happen in the tail.
We need to understand both of those if we want to understand how the magnetosphere works, and we believe that both of those scenarios are also very important for other applications, such as on the Sun, in the solar wind, in planetary magnetospheres, and in many astrophysical objects, as well as in the laboratory.
We hope that it's going to allow us to improve our models so that we can put the right physics in it and actually make predictions about where and when reconnection is going to happen, and this will help us make our space weather models more predictively powerful. The instruments that are actually going to be measuring the particles in space are collecting them much more rapidly at a much higher cadence than they have on previous missions, about a factor of 100. So whereas it would take a previous generation particle instrument about 3 or 4 seconds to build up the whole picture of the sky, it's going to take MMS about 30 milliseconds. So it really is sort of game-changing technology.
The current 24 or so operating satellites will be enhanced with new missions under development. The Japanese Space Agency will be launching their next solar physics satellite, Solar C. The Indian Space Agency will be launching Aditya to study the Sun's coronal mass ejections and magnetic field structures. The Deep Space Climate Observatory will maintain real-time solar wind monitoring capabilities critical to the accuracy and lead time of space weather alerts and forecasts. The European Space Agency's solar orbiter will be launched in 2018 and fly closer to the Sun than the planet Mercury to study how the Sun creates and controls its heliosphere. Also planned for a 2018 launch is NASA's Solar Probe Plus. It will approach the Sun more closely than any other probe before, at just 3.8 million miles from the surface of the star. Scientists have long wanted to send a probe through the Sun's outer atmosphere. The spacecraft will be exposed to temperatures approaching 1,370 degrees Celsius. Together, they will continue to monitor, study, and discover the secrets of this nuclear anvil that supplies us with light and life. Aside from the science, the images captured reveal to us the beauty and power of this, our nearest star, in all its grandeur. The night sky is a time machine. The further we look out into the universe, the further back in time we reach. What we see in the night sky is only a small percentage of the contents of the universe. Most is dark matter and dark energy. We know it exists, but its nature eludes us for the moment. No longer hampered by a hazy, often polluted atmosphere, telescopes and other sensors have been able to obtain clearer images from orbit thanks to advances in technology and engineering. In the 1960s, satellites began to explore the cosmos surrounding us. They saw beyond visible light into ultraviolet, infrared, X-ray, and even gamma rays. Like the universe itself, our understanding of its beginnings, construction, evolution, and future is evolving and constantly expanding. In the last 2 decades of the 20th century, the United States and other nations began to develop more substantial research programs, utilizing larger and more complex space-based telescopes.
For hundreds of years, thousands of years, humans have thought the universe is a very static place. If you go out at night and look into the night sky, you will see that things don't really change much. The universe appeared very static for a long time. We now know this is not true. The universe is a highly dynamic place, and things are happening all the time. Every single second, a star explodes in a gigantic supernova explosion somewhere in the universe. And we have to go and find it. We have to build instruments that are capable of finding those unforeseen events.
The Cosmic Background Explorer, or COBE satellite, started crystallizing the big picture of the universe by mapping the microwave background radiation left over from the early universe. Its successor, WMAP, created the most detailed portrait of the infant universe.
Well, because it takes the light over 13 billion years to reach us, we are seeing now what the universe looked like then, over 13 billion years ago. So it's a fossil remnant of what the early universe was like. And just like fossils are used to study the past, we use this light to study what the universe was like way back near the very beginning.
And you can see in there blue spots and red spots. And what those correspond to are slightly hotter and colder images of the sky. That's a picture there, those hot and cold spots, that pattern is really the afterglow of the Big Bang. On a sort of deeper long-term time level, it's this amazing consistency that the picture we can put together of the universe is relatively simple, that the pieces fit together. It's a stunning confirmation of the study of cosmology for many years now. It's just built up, and here it is. In some ways, we're getting to know the cosmos like we know our own backyards.
ESA's Planck spacecraft joined the fleet and expanded on their observations. Together, they were able to map vast regions in multiple wavelengths, enabling astronomers to determine the size, shape, and age of the known universe.
Just 370,000 years after the universe began in a Big Bang, all that existed was a hot plasma similar to a candle flame. Protons and electrons, seen as the red and green balls, were bouncing around, scattering the light. The particles of light, called photons, shown in blue, couldn't go far without colliding with an electron. As the universe cooled, the protons and electrons could pair up, forming hydrogen atoms, and the light was free to travel. It's been traveling freely ever since, through the dark ages before there were stars, then past the formation of the first stars. As the universe expanded, photons lost energy, changing color. They went past clusters of galaxies. The path of the photon is slightly bent by the gravity of the clusters. Now and then, going through a cluster, an electron, that green ball, would collide with some of the photons. They would change their path, past more matter, more little wiggles due to gravity and mass. The photons traveled for 13.8 billion years before they reached the Planck detectors and died a glorious death, giving up the information that they had gleaned passing through the entire universe to our instruments and enabling us to make this beautiful map of the universe.
The various satellite telescopes have sensors designed for use in multiple wavelengths of the electromagnetic spectrum, from near to far infrared light, through visible and ultraviolet frequencies, to X-ray, gamma, and cosmic ray detectors. Each can reveal unique aspects of the construction of stars, nebulae, galaxies, and the exotic blazars and black holes. However, in the public's eye, the poster pin-up star of the latest generation would undoubtedly be the Hubble Space Telescope. Over its 25-year lifespan, Hubble has produced some of the most amazing imagery of the cosmos as it delves back in time through visible and infrared light. Another advantage of Hubble is its long lifespan, thanks to several maintenance missions, which allows it to study objects over a long period of time with some amazing results. Newborn stars eject streams of matter into the surrounding star-forming region. Known as Herbig-Haro objects, these supersonic jets can be seen to change over a very short time span.
if you see just a single picture from Hubble, you can interpret it in many different ways. But the fact that Hubble has been around for as long as it has been means by taking multiple images, you can actually stitch them together and watch how the material moves. And so that really gives you the only way to get true insight into the physics of the dynamics of what's going on.
The Horsehead Nebula in the Orion constellation, silhouetted by glowing gas, is a good example. Infrared can see right through, revealing its dark secrets. The Spitzer telescope is one of NASA's great observatories.
Spitzer is an infrared telescope, which means it sees through the dust that's out in space. And by seeing through the dust, we get to pinpoint the stellar nurseries that are out there where stars are being born.
We've been flying for about 10 years. That's about 3,600 days. We have 5,000 published papers. That means every day a new paper based on Spitzer data announcing new results and new discoveries is published, which to me is absolutely amazing.
Spitzer has made several surprising revelations within our solar system and beyond. It helped pinpoint some of the most distant galaxies in the universe, and Spitzer's ultra-high-resolution map of the Milky Way substantially improved our understanding of our own galaxy's structure. Japan and ESA had launched their own infrared telescopes in various infrared wavelengths. The European Herschel, in particular, focused on massive star formation regions.
We are really happy to have new things and to understand, trying to understand, because we are making a new step towards our understanding of massive star formation. So the idea is that Herschel can reveal this population of highly embedded stars that are formed in gas and dust cocoon, but that are not visible at optical wavelength, for example. So we need Herschel to detect all this population of very young stars.
The next great spaceborne infrared telescope is the James Webb Telescope, which is nearing test completion in preparation for its launch in 2018. It will have a 6.5-meter primary mirror, almost 3 times larger than Hubble. However, ground-based telescopes are also working in the infrared spectrum.
So there's a large complementarity between space and ground. From space, with the Hubble images, you can characterize the images, you see the images much better. With the ground-based telescopes, you then can take that light and look at spectra and then find the redshifts, for example, for distant galaxies, or you can take infrared observations, which Hubble couldn't do for a long time, to then see how these objects look in the infrared.
Together, they have delved into the star-forming nebulae left over from exploding supernova and witnessed the birth of stars. Another observational tool in the electromagnetic spectrum for astronomers and cosmologists is the X-ray band.
An amazing discovery of the last 20 years is that every galaxy, like our own Milky Way, has a massive black hole at its heart. And as material from this galaxy, dust and gas, falls onto this central black hole, it radiates. And we can see that. So if we look at the sky in visible light, we see stars. If we look at the sky in X-rays, we see black holes.
You can observe X-rays from very distant objects. So you can investigate the cosmic structure of the universe. So you investigate the matter distribution in the universe via observing the galaxies, the black holes in the center of the galaxies to very far distances. And this is very important for cosmology and to learn about the origin and the evolution of our universe.
X-rays are absorbed in our atmosphere, so X-ray detectors must be placed at either high altitudes by balloon or into orbit. NASA's flagship X-ray telescope and one of their great observatories is Chandra.
you want to find black holes, you want to use an X-ray telescope.
What we're tending to find is that a cluster of galaxies has a bright central galaxy in the middle. It's often an active galaxy or a quasar, so a supermassive black hole in the middle of a big galaxy. Because when the cluster is forming, a lot of the material tends to fall to the middle, so you get the biggest galaxy in the middle.
So you see the power of an observatory, an observatory like Chandra with a state-of-the-art telescope and these imaging and spectroscopic capabilities of its science instruments can do things that maybe weren't even things that you planned on doing because you didn't know about them at the time. And a lot of the science with Chandra falls in that category.
The most recent telescope launched is NuSTAR, which has the ability to focus X-rays for a much sharper image. One of NuSTAR's main scientific goals is to make a full census of black holes in the universe. X-rays have also revealed the explosive processes of nova seen only at these wavelengths. ESA have their XMM Newton studying cosmic evolution, and Integral, the International Gamma Ray Astrophysics Laboratory, looking at gamma ray frequencies, revealing unseen structures and new sources of gamma rays.
So Integral is important because it's one of the few satellites which look in gamma rays. And together with other satellites and observatories around the Earth, you can get a complete picture of how these stars evolve. And without Integral, you're missing a large piece of the puzzle. We want to know how did they produce the elements which we are made of. And these are the objects which throw all the different kinds of material into the universe, and they wander off into space. And we are made of all these elements which are produced by the supernova. So it is important for us to know where does life originate and how does it originate.
Gamma rays are at the top of the electromagnetic spectrum, the most energetic and powerful photons which stream from black holes, exploding stars, and even from our own star, the Sun. Originally called GLAST, the Fermi Gamma Ray Space Telescope observes the entire sky in high-energy gamma rays every 3 hours, creating the most detailed map of the universe ever known at these energies. When it detects a new gamma ray burst, it works in conjunction with the SWIFT satellite. Then SWIFT is able to spin rapidly across the sky and point an X-ray telescope and an optical ultraviolet telescope at the possible location of the gamma ray burst.
GLAST is primarily devoted to seeing in a new energy range.
It's designed to pick up at the upper end of the SWIFT energy range and carry it on up to much higher energies.
And it allows you to just see, stranger and more exotic things the further up in energy that you go.
GLAST and SWIFT are very different. SWIFT is like a nimble small satellite that points here and there, but it isn't surveying the whole sky. It's pointing in its particular objects. GLAST looks in the high energy gamma ray sky. It looks over the whole sky at all times.
So when we see something interesting with GLAST, we can ask SWIFT to go look at it with their other telescopes and gain additional information about it.
We don't know what will happen over the next 10 years, hoping that SWIFT will still give us exciting data. But what we do know is that SWIFT will give us exciting new data because of its pure nature. This is what it was built for, to study new, unforeseen, unexpected events, and they will inevitably happen.
There is one more type of radiation being studied in orbit: cosmic rays. The 8-ton cosmic ray particle detector, called the Alpha Magnetic Spectrometer, or AMS instrument, is attached to the International Space Station. Cosmic rays consist of protons, alpha particles, atomic nuclei of heavier elements, electrons, their antimatter partner positrons, and gamma rays. Studying these particles may answer some fundamental questions, like the unexplained absence of antimatter and the nature of dark matter in the universe.
Calibration of positron is important because when you have dark matter collision
with another dark matter, you produce excess positons. So the characteristics of the excess positon tells you what's the origin of dark matter.
About 80% of the matter in the universe is invisible to telescopes. This dark matter neither reflects, absorbs, nor emits light, yet it interacts with matter via a gravitational influence which can be seen in the orbital speeds of stars around galaxies and in the motions of clusters of galaxies. Yet, despite decades of effort, no one knows what this dark matter really is. This visualization shows galaxies composed of gas, stars, and dark matter colliding and forming filaments in the large-scale universe, providing a view of the cosmic web. It is believed that dark matter provides the framework for this web. Galaxy clusters are the largest gravitationally bound structures in the universe. It is also believed that after the Big Bang, the universe originally decelerated in its expansion, but then changed gears and began to accelerate.
Important discoveries in astronomy and astrophysics was the discovery of dark energy, and that is that the universe is accelerating apart. What people are trying to do using various different techniques, and again in all the different wavelength bands, is to measure the parameters to characterize the dark energy.
With a launch date set for 2020, ESA is building Euclid, a space telescope which, it is hoped, will chart dark matter and dark energy's effect on the universe.
I'm working on Euclid. That is a mission to map the universe. And for that we built a highly precise telescope in which we can map dark matter structures as well as derive the properties of the dark energy.
Understanding dark energy will allow us to understand the future of the universe.
The interesting thing is we get more and more dark energy. Why? Because our universe is expanding. And with our expanding universe, we get more dark energy in our universe. Now, the ordinary matter, so dark matter and normal matter, is not expanding, it's diluting. So the fraction of dark energy compared to normal matter is increasing in time. When the universe expands more and more, we get more volume of our universe, we get more space, and we get more dark energy.
The leading particle physics model for dark matter is called weakly interacting massive particles, or also known as WIMPs. These guys just fly through the universe without even bumping into anything or each other. The idea of two WIMPs coming together, annihilating and forming gamma rays is kind of like two bullets hitting head-on in a crossfire. It's very rare. But when you go to the area around a supermassive black hole, we expect the density to be much higher, so the probability of annihilation is much higher in this detection with a gamma ray telescope.
In his theoretical process, Schnittmann's computer simulation shows particles of dark matter around a massive spinning black hole. All of the action takes place close to the black hole's event horizon, the boundary beyond which nothing can escape, in a flattened region called the ergosphere. Within the ergosphere, the black hole's rotation drags space-time along with it, and everything is forced to move in the same direction at nearly the speed of light. Concentrated, fast-moving dark matter particles collide and make gamma rays, but only some of this high-energy light can escape the black hole, in this case from the left side, where the black hole is spinning towards us, giving us a lopsided glow of high-powered gamma rays. The simulation tells astronomers that there is an astrophysically interesting signal they may be able to detect as gamma ray telescopes improve. Schnittmann believes this would be conclusive evidence of the WIMP model.
To me, dark matter, black holes, two of the most elusive things in the universe coming together to help explain each other is quite poetic.
Future missions will see a gravitational wave observatory to study gravity waves and test Einstein's theory of general relativity. The Athena mission, mapping hot gas structures and searching for supermassive black holes, due to launch in 2028. The Sloan Digital Sky Survey, the most ambitious astronomical survey ever undertaken, will provide a three-dimensional map of about 1 million galaxies and quasars. The recently refurbished and upscaled CERN Large Hadron Collider is one of the tools in search of WIMPs and other exotic particles that may help explain the fabric of the cosmos. Then perhaps the scientists, astronomers and engineers can turn their attention to other mysterious theories brought about by particle physics, such as multiple dimensions, entire universes beyond our own, and what lies beyond the event horizon. These in time will become the new frontier.